Let's finish up the factoring component of section 5.4. Follow along here with example 3. So take a look at that example in your textbook. I'm going to do one additional example. Factoring by grouping, hopefully you remember this from Algebra 1. It's also a part of the AC method, so it's not something that's totally foreign. If you remember factoring by grouping, we're going to take a common factor from terms 1 and 2, factor it out, and then take a common factor from terms 3 and 4, factor it out. We should get the same binomials. So between 27x cubed and 45x squared, common factor, I'm thinking 9, x squared. That can be factored out of both of those terms. That leaves me with 3x plus 5. Terms 3 and 4 are not really a common factor there, but the negative sign here indicates I need to factor out a negative. So in this case, you're just going to take out -1. Changes the signs here into positives. That's a good sign. We have matching binomials here. So I'll complete the factoring by grouping, except there's one catch here. The whole premise of this section is basically, is it factored completely? Is this factored completely? 3x plus 5 is definitely done. Look at 9x squared minus 1. That should ring a bell in your head as a potential difference of squares. 9 and 1, both perfect squares, and we have a subtraction between them. So if it's a squared minus b squared, it's going to factor as a plus b, a minus b. In this case, it's going to factor into 3x plus 1, 3x minus 1. We'll keep the 3x plus 5 as is. Now is that factored completely? Yes, that one is finally done. So factored by grouping. Let's jump down here. Factoring in quadratic form. I put the quadratic in quotations because it takes on the appearance of quadratic form, although it doesn't have your typical x squared, x, and a constant. Let's look at this one on the left over here. As I said in yesterday's lesson, I cannot stress enough, you have to look for a GCF first. So obviously we have two 10s here. Let's factor out 10, see what happens. If I take out 10, I'm left with x to the 4th power minus 1. So even though it's not x squared minus 1, which we know would factor as a difference of squares, x to the 4th is also a perfect square. So what I'm going to do here is say that the a value as a part of a squared minus b squared, instead of x, it's actually going to be x squared. So if I factor this in the difference of squares pattern, don't forget your GCF at first. But this is actually going to turn into x squared plus 1, x squared minus 1. Are we done factoring completely? Take a look. 10 is just a GCF. X squared plus 1, nothing I can do with that. X squared minus 1 is a regular difference of squares that you've seen before. So, final answer, factored completely. X plus 1, x minus 1. Take one more scan at that, but that one is definitely factored completely. Nothing else I can do with that. One more example for you. 3m squared plus 54m to the 7th power plus 51m squared. Obviously you're going to look for a GCF to start this one. And let's try 3. I can't take out a number bigger than 3 because of this coefficient. And as far as variables go, I've got m to the 12th, m to the 7th, m to the 2nd. So when I take out 3 m to the 2nd, what's remaining is m to the 10th power. 54 divided by 3 is 18. I took away 2 m's from 7, that leaves me with 5. And then took out 3 from 51, that leaves me with 17. And I took 2 m's away from 2 m's, so it's just a constant 17. Okay, m to the 10th, m to the 5th, those are bigger exponents than we're used to factoring with. However, does this model, let's just, in your head, change that m to the 10th to m to the 2nd. Change the m to the 5th to just regular m, and the 17 will stay the same. Would that model the quadratic form? It does. This m to the 10th is double the amount of exponential powers as this one right here. So what I'm going to do is, let's just, for a moment, let's pretend that this is a 2. I'm going to change it back. what are factors of 17 that sum to 18? It's nice that we have two positives right here. Well, that's just going to be 17 and 1. 17 is a prime number. So I would make that m plus 17, m plus 1, and that would be done. We do have to account for the fact that this was m to the 10th and m to the 5th. Now, in order to get m to the 10th as the first term here, it would have to be m to the 5th times m to the 5th. Remember that when you have the same base, the exponents add together. So finally, and let's check it. Let's check 3m squared. That's done. M to the 5th plus 17, I can't factor that. M to the 5th plus 1, I can't factor that. So that one is factored completely. Definitely something a little bit new here, but this is all as a part of factoring something completely.